Hello class, this is section 4.4 and we are going to talk about how to model a vibrating string with fixed ends. So here's our problem. We have the vibrating string equation that we have discussed previously. One thing to note, we have written down the constant as c squared. Previously the constant was written down as T over rho, tension over density. And we are just going to rewrite it as c squared just to make our calculations a little bit easier. So let's consider what this equation is saying. We have the boundary conditions u0t equals ult equals 0, and that simply means that our string is fixed on both ends at the same height. We call that height 0, and that's going to be true for all time. So the boundaries of the string don't change. We also have two initial conditions. We know that the initial position of the string is given by a function fx, but we also know the derivative of the string. So remember that you can think of u here as the height of the string at position x. So we know exactly how the string behaves in terms of its height at every point and its velocity at every point. We need two initial conditions in terms of t because we have a second derivative with respect to t in this problem. This contrasts with our heat equation, which only had a single derivative with respect to t, and that is why we only needed one initial condition. The first step, once more, is to find the product solutions. These are going to be written in the form uxt equals fxgt. Now we plug them in to our vibrating string equation, and we obtain fx second derivative with respect to t equals c squared f second derivative with respect to x times gt. And this simplifies. If we move all the t's to the left and all the x terms to the right, we get 1 over gt times g double prime t, let's also put a c squared over here, equals to f double prime x 1 over fx. So the left hand side is constant with respect to x, and the right hand side is constant with respect to t, and since they're equal, both sides has to be constant with both x and t, and therefore it's just a constant. Now we want to introduce a minus sign for this lambda, and the reason simply is that the f will be our boundary value problem, and we prefer to write down our boundary value problem in this form just to keep it standard with our previous equations. So now we have again reduced our PDE into two ODEs, and let's see how to deal with them. The first ODE is one that we've done already several times in the past. We have, for our boundary value problem, f double prime x plus lambda fx equals 0, and our boundary values are going to be 0 on both sides. So we have f0 equals 0, f lambda L equals 0. And we know that this has eigenvalue n pi over L squared for 1, 2, 3, and so on, with eigenfunctions given by the sign of n pi over L x. So that is our boundary value problem, and let's figure out how to solve the other differential equation. And this one is given by g double prime t plus lambda c squared gt equals 0. And this one we can solve by our usual g equals ERT method. We get r squared plus lambda c squared equals 0. Taking square roots, we get r is equal to plus or minus I times square root of lambda times c. And this means that if we take the general solution of g, we get that g is going to be equal to c1 cosine of square root of lambda ct plus c2 of sine square root of lambda ct. And this solves our other equation. Then we know that product solutions are of the form fx times gt, and fx is just sine, and gt is both cosine and sine, lambda ct. So we can write down our product solutions as, let me write it down this way. So un of xt equals fx is just sine and pi x over L. But here we have the option of either including a cosine or a sine for ugt. So let's just write them down both. So un c for cosine. This can be cosine, and square root of lambda is going to be, lambda is n pi over L squared, so square root of lambda is just n pi over L. So you get n pi over L times c times t. And also we have another option where we can do the sine instead. Equals sine n pi x over L times sine n pi over L c t. And these are our options for product solutions. And this means that, in general, our solution uxt can be written down as something like this, just a linear combination of all the possible product solutions. The next question we have to ask is, what are the constants an and bn? Again, we have to derive them from the initial conditions. So we have that ux naught equals fx, and partial u partial t equals gx. So let's plug that in. Ux naught equals fx. However, also, since sine of 0 is 0, you can just ignore all the bn terms, and we are left with n equals 1, infinity, an sine n pi x over L. Remember that cosine of 0 is 1, so we're just left with this. So this is equal to fx. And it turns out that we precisely just get the sine Fourier series of f. And as we've done before, this is just going to be equal to an equals 2 over L integral from 0 to L fx sine n pi x over L dx, exactly the sine Fourier series of fx. Now let's consider instead the other initial condition, partial u partial t ux naught. Oh, before we do that, we should probably figure out what the t derivative of uxt is for us. This is going to be summation from infinity n equals 1. So remember, we're differentiating with respect to t. So all the stuff with x's in them remain the same. This becomes differentiating cosine of n pi L ct. So we're going to have to pull out the constant, n pi c over L times minus sine n pi c over lt. There's enough brackets, I think. Yes. And then for the bn terms, we're going to get bn. Again, the sine term remains unchanged, but the second sine term, we're going to have to pull out the constant, n pi c over L times cosine of n pi c over lt. That's our derivative, and our initial condition is of derivative x with t equals 0, the initial condition with respect to time. So this means that, this should be just partial t u x 0, plugging in 0 here. So again, sine of 0 is 0, cosine of 0 is 1. So we're just left with the bn terms. The an terms will go away conveniently, and we have bn sine n pi x over L times n pi c over L times 1. And this is equal to g of x by our initial condition. But this just means that we are looking at the sine Fourier series of this function, bn sine n pi x over L So the sine Fourier series of L gx over n pi c. And yeah, that's another thing that we've already done. So we know this is actually equal to 2 over L times integral from L to naught of the function L over n pi c times gx sine n pi x over L dx. And this is how we solve the vibrating string equation with fixed ends.